Hello, my name is Matt Peister, and I'm from the Alliance for Youth Climate Leadership. And today I'm going to give a short example of what one of our lessons could look like, or if you want to just take this information and do it yourself, you're more than welcome to as well. And again, we can specialize these if you want something more specialized. So typically I would come into a classroom and I'd start with some type of icebreaker. So this one is an example for say your name. Everyone would say their name as well as a quick noise that kind of just describes the emotions or feelings that they're having at that moment. Just a good way to kind of like open up a little bit. And sometimes it's better than words in some cases to get across your emotions. So it could be a "Ugh," or whatever you want. Um, After that, then I would say we're going to play a little game. And we dive into this game. I call it How Close Can You Get? Not the most creative name, but it's basically 20 questions. And the idea is that I would, as the teacher, I would think of a day, or you can have one of the students think of a day in the last 10,000 years. I typically choose somewhere in the last few decades, but I think of it in my brain and I say, can you guess the date? Of course, no one's going to be able to guess one date out of the last 10,000 years. And you say, well, if you can't go into my brain directly and just have me tell you the date, then how are you going to get it? One way is that you can ask me questions that won't directly figure it out, but it'll give you a better idea, such as by doing 20 questions and asking things like, was it before I was born? Was it after I was born? Yes and no questions like that. And so you'll have the class go through that, and you'll actually find that relatively quickly, people are generally able to figure out within a few days at least the date that you have. So from 10,000 years of dates, very often with just a few questions, people can indirectly figure out that your date is whatever it is. Maybe it's January 20th, 1984, something like that. And you'll go from that and you'll say, okay, so we were able to figure that out without actually directly measuring my date, right? We figured it out by asking kind of tangential questions. And that's going to come into play because we're going to be talking about historic versus modern temperature. We're going to be talking about climate proxies. Many of them probably will not know what a climate proxy is, but you'll say, here's an example of a graph. It goes back almost 2,000 years, and it shows changes in temperature according to Celsius. But here's the thing, in 200 AD, do you think there was a bunch of scientists standing outside with a really accurate thermometer taking the temperature? Probably not. So how did we get this information? And you can also just ask, what do you notice about this graph first? That's usually a good idea just for people to zoom in for a second. Maybe they notice that it jumps up at the end. Maybe they notice that it only goes a few degrees change. Maybe they notice it covers almost 2,000 years. Just what do you notice usually gets some good interest into it. And then again, you say, how did the scientists figure out these temperatures when we didn't necessarily have scientists actually directly measuring it? Well, that kind of leads back to our game, and that leads to proxies. And a proxy is an indirect, in this case, it's an indirect measurement. So a climate proxy isn't figuring out the temperature or the climate of an area, even though we can't actually go back in time and measure it. So we have to figure it out through odd questions in really creative ways. And so we're going to go with that climate proxy and give them a few examples. So some examples of climate proxies could be that people use ice cores. There's air that gets trapped in bubbles of ice up in the poles, and it stays constant. It doesn't change. That pocket of air stays the same for thousands or millions of years, right? And then if a scientist goes and sticks, basically gets that air, digs into the ice and gets that air, they can measure like the carbon dioxide levels or the oxygen isotopes in those ice cores. And by doing that, they can figure out, well, as we know, more carbon dioxide, more greenhouse gases usually means hotter. So they can use how much carbon dioxide is trapped in that air from thousands or millions of years ago to kind of make a guesstimate about what the temperature would have been. They can also figure this out, guesstimates for the temperature and the climate, through lake freezing and thawing cycles, old records about when they would freeze and when they would thaw, so when it got warmer, colder in the year. They can figure it out with pollen records and fossils, or pack rat middens, which are basically just piles of debris, garbage collected by pat rats, because both of these will show what type of plants were alive at a certain point in history. And if you know how the plant survives, what temperature it needs, you can figure out what temperature that area was. So all of these, just like the questions that the students might have asked during that 20 question session, none of them are going to necessarily give you the exact temperature, like none of the questions gave exact dates, but they'll give scientists a ballpark range to look into. You know, we think it was somewhere around this temperature. And the last one I have here is going to be beetles. And this one's bolded because I'm not going to go in depth with all these, because each one of these could be an entire class by itself, just talking about how it works and why we created it and why we think it works. Instead, I'm going to just dive deep into one to give you a taste of what a climate proxy can look like. And then that'll kind of help you understand a little bit just maybe how other climate proxies might work, or just to understand how much work goes into them. They're very educated guesses, not just guesses. So for beetles, we're going to be doing that in a second. And we notice on this graph, basically, as I said, each one of these proxies is kind of a ballpark guesstimate. But when you combine a bunch of different proxies, which is essentially what these different lines are, then that's when we see, all these ballpark guesses match up in this one area. That's very likely what the temperature is. We're coming at it from a bunch of different angles, just like you did in the game. You're getting a bunch of different questions and they're all pointing towards the same date, or in this case, a lot of proxies pointing towards the same temperature. So beetles, I chose them actually because I just think beetles are cool. This is a Hercules beetle that I found down in Maryland when I was traveling once. As you can see, it's about the size of my thumb, and it's just a totally crazy or wild beetle. Beetles are really cool, basically. And they're used in climate proxies in a really interesting way. So I'm going to do a really simple explanation first, and then I'll dive in for a deeper explanation. This is a very simplified version of how you might figure out climate data based on beetles. And the general idea used with beetles is that you find a species of beetles. In this case, it was Diachelia arctica. I might not be saying that right, but right here. You find a species today and you map out where it's found. And then you go and find the fossils of their ancestors, of the same beetles, but thousands or even millions of years ago. You find where the fossils are. And in this case, the beetles today are found here, up at the top where it says modern distribution. But in the past, they were found down here where it says fossil distribution. And what this is indicating, and I'll explain why in a little bit, but what it's indicating is that the temperature where the beetles are found today, it must have been that temperature, or is very likely that it was that temperature when they lived where the fossils were found. So today's temperature where they're living here is probably the same as the temperature of the past when the beetles lived down in the fossil area. So that's a guesstimate, educated guesstimate way of saying, we think we know what the temperature used to be down here, because we think it's the same temperature as what it is now up here in the model distribution. So that's kind of a big what if, though. There's not, the way I've explained it so far, there could be many reasons why they've moved. So let me go a little bit more in depth about why scientists are using this as a method and why they believe that it's accurate. So again, we're studying beetles. This temperature data actually can go back 2.6 million years. And we're comparing the locations of ancient versus modern beetles to figure out that temperature data of historic temperatures. Why do we think this works? So beetles have a very narrow temperature and humidity range that they survive in. So basically it's saying a beetle is good at surviving in this temperature, but not in this temperature, if this was a sliding scale. And same for humidity. So if they survived down where the fossil distribution was, hundreds of thousands of years ago, then that must mean that the temperature there was the temperature of the area where they're now found. Also, they're very mobile physically and dietary wise, a lot of them are. And so they're able to, as temperatures change, the beetles are able to follow the temperature change. So you would be able to, they're basically able to keep up with the temperature. So they're able to move as it gets warmer up higher, then they're able to move with that temperature. And that's why they're now found up here, because they're able to move easily and able to find food easily. Many of the species are still existing, extant, meaning they have not gone extinct. So many of those species are still extant, and for them, a lot of their physical characteristics and temperature, we believe, are actually the same as they were many, many years ago, because they don't really seem to evolve very quickly, because they are so mobile and they have such a wide range of dietary choices. Basically, they're very similar today as they were in the past. So we think that the temperature that they survive at today is probably very similar to what the temperature was hundreds of thousands or millions of years ago, where we found the fossils. Also, there's a high diversity, a very high diversity of beetles. So while our example only had one species, typically we would be using way more than one species at a time, maybe 100 species at a time, to really triangulate the temperature gradient, see where they overlap, and make sure that there's all the species that lived here are now living up here. So it really highlights that temperature as the deciding factor. Also, they're well preserved and easily identifiable. So when we look at the fossils, basically we can identify them easily. You only need a fragment of their body to be able to identify them. And lastly, they're a highly studied order, beetles in general. So we already have a bunch of data about their required temperatures or humidity, which kind of goes back to the narrow temperature and humidity ranges. So they're highly studied, well preserved, and easily identifiable. There's a high diversity. There are species still present today that were present, up to millions of years ago. They're very mobile, and also they have a narrow temperature and humidity range in which they survive. So how is all of that what's the process though of figuring out, other than just there's beetles here today and we found fossils here? To go a little bit more in depth with that, just again to show you how much work goes into this, it's really a lot of work to get these proxies done well. It starts off with a modern data set for summer and winter temperatures of beetles. So this is where the highly studied part comes in. And we figure out what are the summer and winter temperatures that beetles today survive. Where do they move to? Where do they stay? What are the temperatures that they need to survive? And then we go to collect soil samples from historic sites. So people will go and find large soil samples, and they'll sort through it looking for these fossils for historic beetles. And they'll try and isolate the beetles from that soil sample. And then they'll ID those species. Having 100 species in the soil sample identified is common. So not just one like we had in our example, but 100 species, different species. And then we'll carbon date those fossils. And that lets us figure out how old the fossils are. So we know what species they are and how old they are. And then we just compare that to the modern set. And we say we found Diachela arctica down here in the fossil distribution, and we also found it up here. And then we compare the temperatures to say that again. The temperature of our modern distribution, the temperature today is probably equivalent to what the temperature in our fossil distribution was many years ago. But again, nothing is perfect, and there definitely are some problems with this proxy. And so what are some of the limitations of it? First of all, only about 50 to 75% of the species found in the fossil record are actually identified. While it's easy to find them or identify them, it's still sometimes you're not able to. So not all of the species are identified, so we're losing a little bit of data there. And then also mainly predatory and scavenger beetles are actually the ones that are used for this because they're able to very quickly go to new habitats. So when the temperature is changing, these are some of the fastest to move. So they'll stay up to date with the temperature changes. So we're focused on those, again, losing some data by not focusing on other beetles. But we do that because this helps us focus with the quickest reaction, in theory, to temperature changes. Overwintering is also a problem. While a beetle may only be able to survive in this temperature, some of them are able to overwinter in microhabitats, or they have some adaptations that let them survive in colder winters than they normally would be able to. So you might find fossils in a place that is misleading. And lastly, it's a proxy. We're not directly measuring the temperature. We're getting an educated guess here. But again, that's the thing about this is you don't just say we believe climate change is real because of this beetle study. You get this study and a bunch of other proxies, and you combine their data together to figure out, oh, the overall trend actually is showing, even with outliers, the overall trend is actually showing that we have been significantly increasing in temperature. And so that's when we combine it with the CO2 concentration in ice, the oxygen isotopes in ice cores, lake freezing and thawing, basically these other proxies that each of them has an incredibly complex and scientific process, just like the beetles do. And that leads us back to our modern versus historic temperatures. And so here, again, each of these lines is actually a study that has various proxies that they gathered data from in order to figure out what they think the temperatures were here, leading up to where we have actual direct measurements. And as I said, the general trend here, while there is some up here and some down here, some down here, some up here, the general trend actually stays right about here. It's relatively consistent throughout. And why this is important, as some people may have noticed, the temperature anomaly here, it only goes up 0.8 degrees Celsius or almost about 1 degree Celsius down. It's around here. That doesn't sound like a lot, 1 degree change in difference. Scientists are worried about a few changes in Celsius degrees. The reason why that's actually important is that, shockingly, the Ice Age, when there was mile-high glaciers in New Hampshire, the entire New Hampshire covered in mile-high glaciers, that was actually only a difference of 4 to 7 degrees Celsius. So 4 to 7 degrees. That's the change. So when scientists are worried about the fact that we've risen, 1 degree Celsius over the last short span of years, it doesn't sound like a lot until you put that in perspective and realize a global change of that much temperature can have very significant consequences. And we learn about historic temperatures through our climate proxies. So the next thing is I would typically have a 5-minute breakout room where I just let people, we've been talking about climate change and proxies, but now just on a spectrum, how much do the students trust this data especially hearing about how much effort goes into it. Do you find it believable enough to make policy change based on your belief in order to, fund renewable energy, try and cut back on greenhouse gases? Give them 5 minutes to just talk with their peers about their beliefs, their disbeliefs, how things may have changed over the course of this lesson, all of that. And then come back together and share if that is appropriate for your classroom culture. And so then you have space for questions, which you could do before the breakout rooms, or you could do after, however you want to do it. And then you can give them this opportunity or a different opportunity. This is one where, as it says, there are handwritten historical records of weather patterns. And in order to figure out climate change data, you can go online and transcribe what it says onto a electronic version so that real scientists can use that data to try and figure out more about climate change. So this is something your students could actually do. Again, just donating information or donating their time to help scientists figure out climate change. And then here are some sources that I have at the end. So again, this is a talk about climate proxies. And my name is Matt Peister, and I'm from the Alliance for Youth Climate Leadership. If you have any questions about this or about anything else, just feel free to reach on out to us. And I hope that this was informative enough that perhaps you'll find use for it in your classroom, or you'll ask us to come in and do something similar for your classroom. Have a good day.